Okay, so I'm going to give a bit of an introduction to this area that that some people call information geometry. Okay, and just to this is a lot of what I'm talking about is often described as the maximum entropy principle or maximum entropy methods, and these have been very successful in natural language processing and are now being used in other areas as well, like computational biology. I'll introduce it by a sort of a toy example. Okay, sort of a clean toy example. Okay? So suppose you want to model the distribution of English words. Okay, so for instance, you might be an alien who has just arrived on this planet, and you notice you find this dictionary. You see that there are all these words over there, and you want to model the distribution over words. You want to know which ones are frequent, which ones are not frequent. So a priori, you don't know anything. You just know that there are these, 50,000 words or whatever. And so, in the absence of any further knowledge, the sort of default thing you might do is to just pick the uniform distribution, to just say that everything's equally likely. Okay? But now you can collect some samples, and you notice a few things. For instance, you might notice, okay, well, there aren't so many words whose length in random samples of words, only about 30% of them have length more than 5. It's a little observation you make, from these small samples that you take. You might say that, okay, in a random sample, the probability of a word ending in E, the fraction of words that ends in E, is about 0.45. Okay, and you notice a few other things like this. You keep track of a few features. And now the question is, how do you adjust your distribution accordingly? So initially you knew nothing. You picked the uniform distribution. Now which distribution do you pick? You've got a little bit of data, but that's all. Okay, what's the right thing to do now? Okay, so it turns out that this particular question will, this toy example will let us develop three sort of theories that are closely interrelated, having to do with entropy, exponential families, and information projection. And it'll help us understand the connection between these three things. Okay, so it's a nice excuse to actually develop, to sort of theoretically develop these three areas and see what the connections are between them. Okay, so let's start with entropy. Okay, so what was our question? Let's try and pin down this question. Let's try and formalize it a little bit. So we have some domain, which in that example was English words. Okay, so, just a big list of words, 50,000 words, say, or, 100,000 words. And now, from a small random sample or whatever, we did notice a few things. And we can think of that as measuring a few features of each word. Okay, so for instance, let me see if I can work this thing. Yeah, so, for instance, we were measuring whether the length of a word is more than 5. Okay, so we had this indicator feature, which was 1 if the length is more than 5 and 0 otherwise. And we noticed that the probability of this happening, the probability of the length being more than 5, was 0.3. In other words, the expectation of this feature, the expectation of t was 0.3. Okay, so the expectation of this indicated variable is just the probability that the length is more than 5. Okay, and we noticed that that was 0.3. We measured a few other things. For instance, we had another feature which just checked whether a word ends in E. And we noticed that the expectation of that feature was 0.5. And we had a few more things like this. Okay? So we've now got a bunch of constraints. And we want to continue our previous methodology. We started knowing nothing, and we just picked a uniform distribution over all the words. Now we know a few things, and we still want to, so we want to model these. We want it to be the case that the new distribution we pick does satisfy these things that we've observed, but other than that assumes nothing. So other than that is as random as possible. Okay? So what is the sort of, what is the single distribution, or maybe it's not unique, but what is the distribution that satisfies these constraints, but otherwise makes no assumptions? Okay? Or otherwise is as random as possible. Okay, so, by the way, stop me at any time if there are any questions at all. Okay? So in order to do this, so we formalized a lot of it. We formalized what our constraints are. We want a distribution that satisfies certain expected value constraints. The next thing we have to formalize, the only thing we really need to pin down now is, what do I mean by random when I say a distribution that's as random as possible? Okay? So what is the randomness in a distribution? What's the randomness content of a distribution? So how would we define randomness? This seems like something that, there's got to be a lot of disagreement about this. There must be lots of ways to define randomness, So how would we go about it? So intuitively, let's think of some things that we would like to be true of any reasonable definition of randomness. Okay, so for instance, it's natural to think of a fair coin as having one bit of randomness. Okay, the outcome is either a 0 or a 1. They're equally likely. It's very natural to think of that as being one bit of randomness. Okay, what if a coin is biased? Well, if a coin is biased, if it's more likely to, say, turn up heads, then it's less random. So if we've said that a fair coin is one bit of randomness, then a biased coin, its randomness content should be strictly less than 1. Okay, so that's something we would like to be true. What about two independent fair coins? So now this is 2 bits of randomness. Okay, because they're independent of each other. They each contain separate amount of information. If one of them is 1 bit, 2 of them should be 2 bits. What if the fair coins are dependent? Okay, so the outcome of the second coin depends on the first coin. Well, then the overall randomness is less than 2 bits. Okay, for instance, the second coin might be exactly equal to the first coin, in which case there's just 1 bit of randomness in them. Okay? And here's another thing we'd like to be true, sort of extending these things. Suppose we have a uniform distribution over 32 possible outcomes. Well, this is something we can code in 5 bits, each of which is equally plausible. Okay, so we would like this. We would like to say that this has 5 bits of randomness. Okay, so these are some of the sort of intuitive things that we would like a measure of randomness to capture. But just putting down a few things like this, there's got to be a million ways to define randomness, right? So there's one, however, that seems to be really popular. Okay, there's one that there's one that everyone seems to use, and it's called the entropy. Okay, so suppose you have a discrete distribution, x. So x is some random variable which takes on discrete values, and it's got a distribution p. Then the entropy of it is this weird thing. Okay, it's the sum over all possibilities of x of p of x log 1 over p of x. Okay, which is expectation with respect to, another way to write it is just the expectation with respect to random draws from p of log 1 over p of x. Okay, so this is the definition that people seem to use. And just looking at it, it looks a little crazy. How can this be the natural notion of randomness? P log 1 over px. What is this thing, right? So let's first check that it isn't totally crazy. Okay, let's just plug in a few examples and see that it's actually doing the right thing in at least in at least some toy cases. So for instance, if we look at a fair coin, then there are 2 possible outcomes, each with probability a half. So the entropy is a half log 2 plus a half log 2, which is 1. Okay, so that's something we wanted, that the entropy of a fair coin is 1. Now suppose we have a coin with a bias of 3/4. So then we get 3/4 log 4/3 plus a quarter, which is the other outcome, log 4. And that turns out to be less than 1. It turns out to be 0.81. Okay, so again, this is what we expected. Now, we knew it should be less than 1. We didn't know how much less than 1. But 0.81, sure, whatever. Okay, that's plausible. What about a coin with bias 0.99? Now, this is a coin that's almost not random at all. It's a coin that is almost deterministic. So we would expect that the randomness content of this is something that should be very small. So let's plug it in. It should certainly be smaller than a coin with bias 3/4. So let's plug in 0.99. We get 0.99 log 1 over 0.99, and we plug it in, and it becomes 0.08. Okay? So that's good. It's close to 0, which is what we would want. And it's much less than these 2 numbers. Okay, and finally, let's check a uniform distribution over k outcomes. If it's a uniform distribution, all these probabilities are 1 over k. So we get 1 over k log k, and now we sum it over k things, so the answer is log k. Okay? So in these basic cases, this is doing the right thing. Now, I mean, qualitatively, it's doing the right thing. We know that this should be smaller than 1, and we know 0.8 should be the smallest of all, and that should be fairly close to 0. So qualitatively, it's doing the right thing. But again, I'm sure I could cook up, hundreds of other measures that also qualitatively do the right thing on these examples. Okay, so what's special about this one? So let's take a closer look at it. At least it's passed the first round of tests, and let's get a little more of a sense of what it's like. So first of all, this thing is concave. Okay, so if you actually just draw the graph of it, this is for a case of a coin with bias p. It's a concave thing. It's maximized when the coin is exactly a fair coin, at which point the entropy is 1. Okay? If the coin is totally deterministic, if it's always heads or it's always tails, then the entropy is 0, which is what we'd expect. There's no randomness at all. And it's symmetric. A coin with bias 3/4 is the same as a coin with biased 1/4 in terms of its randomness content. Okay, so this is perfectly reasonable. In that sense, it's fine. So let's look at some of the nice properties that this thing has got. Okay, so what are the intuitive properties that this thing has? So first of all, entropy has got expansibility. Okay, so for instance, suppose I have a distribution which has n possible outcomes with some probabilities, p1 through pn. Now, I add another fake outcome that never occurs. Okay, so there are n outcomes, and they have some probabilities, and now I just tack on another fake outcome which just never happens. That clearly should not change the entropy. And that's true. The entropy remains the same in that situation. Okay? It's got this property of symmetry, which is that if you have a distribution which, if you just permute the labels of the points, then the entropy doesn't change, right? And is this? So that's that's not the way. So. Right. So this is clear, right? So the notion of randomness should not be sensitive to the names you actually give things. Okay. If you flip heads and tails, randomness should not change, and that's the property of symmetry. It's also got this property of additivity, and this is a very useful thing. Okay. So if you have two independent random variables, then the entropy of them taken together is the sum of the individual entropies. And let's see why this is the case. Okay, so I have these two things that are independent, and now I want to look at their joint entropy, the sum of them taken together. Well, that's the sum over all possible outcomes, x and y. Just plug into the definition, p of x log 1 over p of xy. But in this case, because of independence, p of xy is p of x times p of y. And so, and because it's a log, I can split this into its two pieces, log 1 over p of x plus log 1 over p of y. So I get these two individual summations, and I can now sum out the y, and in this case, I can sum out the x. Okay, so I get the individual entropy of x plus the individual entropy of y. Okay. Great. So this is another of the properties we wanted. Now, what if the variables are not independent? In that case, we want it to be the case that the entropy of the joint distribution is at most the sum of the individual entropies. Okay, so we wanted and that's called subadditivity. Okay, so if they're independent, then the entropy of the joint is just the sum of the individual entropies. If they're dependent, then it's going to be less than that, and that's another good property that it's got. We've normalized it so that a fair coin has entropy 1. Okay, you could just scale it by an arbitrary constant. A reasonable normalization is just to say fair coin is entropy 1. And finally, we want it to be the case that as the bias of a coin goes to 0, the entropy also goes to 0. Okay, as it becomes more deterministic, the entropy goes to 0. And it also has that property. So it's got these 6 properties. that we think, that intuitively should be true of any measure of randomness. But now it turns out that entropy is the only measure that satisfies these. Okay, so if you proceed in an axiomatic way, if you say, look, I want to come up with a measure of randomness, and now let me put down a few properties that any measure of randomness should have. All very reasonable sounding properties. Okay, what were they? Expansibility. That's totally reasonable. If you add on a fake new sample, if you add on a fake new outcome that never occurs, sure, that should not change the entropy. Symmetry, additivity, subadditivity, normalization. These are very, these are things that, we would think, of course this should be true of a measure of randomness. But entropy is the only one that satisfies all of them. Okay, and so this justifies why we use something with that weird functional form, p log 1 over p. It seems a little crazy at first, but this is why we are stuck with it. Okay, and this is why we have to deal with the thing. Okay, so let's look at some other properties of this measure. First of all, it's closely related to the KL divergence. So some of you might already know this distance measure. It's a very commonly used distance measure between probability distributions. Okay, so suppose I have two probability distributions P and Q, and I want to measure the distance between them. Now, there are many ways one could do it. One could, for instance, draw the curves for P and Q and look at the area between the curves. That's a very intuitive way to do it, and that's L1 distance. Okay? One could look at the L2 distance between them. Or one could, for some reason, plug it into this formula that looks a lot more weird than any of those other two possibilities. And it turns out that this is something that is that's very widely used in statistics. Okay? So what are the features of this? What are the properties of this? Well, first of all, it has many unpleasant aspects to it. Okay, so first of all, it's not symmetric. The distance from P to Q is not the same as the distance from Q to P. It's not at all a desirable thing. This thing could easily be infinite. If it's the case that Q is 0 at a point where P is non-zero, then this whole thing becomes infinite. Okay, so already there are many reasons not to like it, but at least it's the case that it's always positive, and it's 0 only if P and Q are equal. Okay, so this distribution turns out to be very useful in many contexts. Like entropy, when you're dealing with a product distribution, the product in here, the log and the product interact very nicely. And so when you're dealing with product distributions, this turns out to be a very convenient functional form. Okay? In the same way as we saw the additivity property for entropy. Okay? And also, this is closely related to maximum likelihood. If you have a bunch of data and you have some parameterized models and you want to pick the maximum likelihood model, picking the maximum likelihood model is the same as picking the model that has the smallest KL divergence to the empirical distribution. That's the distribution where you just take your data points and assign them all the same way. Okay? So this is so how is this thing related to entropy? To do that, we look at to see how the KL divergence is related to the entropy of a distribution P. So let's say a random variable x has distribution P. Let's look at the KL divergence from P to the uniform distribution. Okay, so that's just plugging into the formula for KL divergence. That's P log P over the uniform distribution. Uniform is just 1 over S everywhere. Okay, so there are S possible outcomes. And so, and again, the log decomposes nicely, and we get P log P plus P log S. Okay? In other words, log S minus the entropy of X. So what this means is the entropy is really telling us the distance from the uniform distribution, measured according to this distance measure, the KL divergence. And just this one formula tells us many things. For instance, it tells us, we know that the KL divergence is always positive. So this tells us that the entropy can never be more than log S. This is an upper bound on the entropy. It tells us that the maximum entropy distribution, we know the most the entropy can be is log S. And when is the entropy log S? When we are looking at a uniform distribution over S outcomes. So the distribution that maximizes the entropy is just the uniform distribution over all of these outcomes. Okay? So any questions about this sort of thing? Okay. So let's look at one more justification of entropy, and then apply it to our problem. Okay. So to understand this, maybe the way to say it is that when you have a distribution and you take one sample from it, there's so much stochasticity in what your output could be. If it's a distribution over coins and the coin is bias 0.75, it could either be 0 or 1. There's a lot of randomness in what the output could be. It's not. So one way to make it is one way to come to reduce the level of stochasticity is to draw many samples. That's when you get a more accurate picture. That's how you reduce the stochasticity in what you're seeing. Okay. So suppose we have a bunch of draws from some distribution. So x1, x2, xn are IID draws from some distribution P. Okay? And now we've drawn a lot of them, and so we can look at the sequences that we get. So if these are coin flips, we just have these sequences 0, 0, 0, 1, 1, 1, etc. Okay? Just long sequences of zeros and ones. So now let's look at these sequences and just put them into two groups. We'll just pick out the sequences whose probability is roughly 2 to the minus this, okay, according to our distribution, and all other sequences. And it turns out that most of the sequences that we observe are going to have roughly the same probability. Okay? This is called the asymptotic equipartition property. So what this is saying is that if you look at the space of all the sequences that you can possibly generate, okay, so in the case of a coin with, say, bias 3/4, okay, this is all 2 to the n sequences. These are all the sequences of zeros and ones you can possibly generate. There are just a few of them that are typical. And these are the sequences whose probability is about 2 to the minus n times the entropy of one of those random variables. Okay, in this case, the entropy of a coin with whatever bias I said, I think 0.6 or 0.75. Okay, so although there's a large space of possible outcomes, there is actually a typical set. And when you draw a large number of sequences, although, so when you draw a large number of points, although the distribution of any one point is really stochastic, when you draw a large number of points and look at the sequences, it's a little bit like a uniform distribution over about 2 to the nh outcomes. Okay, so the distribution it's almost like a flat distribution over a smaller set of outcomes. Okay, so instead of 2 to the n outcomes, 2 to the n times the entropy, which is going to be at most 1 in the case of a coin flip. Okay? So in this sense, the entropy tells us the volume of this typical set. This typical set has volume 2 to the n times entropy. Okay, so let's look at some examples of this, right? So for instance, a fair coin. If we draw n samples from a fair coin, and we look at the sequences we get, well, then we just have a uniform distribution over all possible outcomes. Okay? So in that case, we just occupy this whole space. All possible outcomes are about equally likely, and each of them has, the entropy is 1 in that case, and each of them has probability 2 to the minus n. Okay, so the number of outcomes is 2 to the n. Now let's look at a biased coin. Suppose we look at a coin with bias 3/4. In this case, when you draw a lot of them, when you flip a lot of coins, you're going to find that in the end, about 3/4 of them are heads. Okay, so the typical probability of a sequence like this is going to be about 3/4 of the 3/4 n of the coin tosses are going to be heads, and the remaining ones are going to be tails. Okay, and this is the typical probability. Most of the sequences will conform to this. Okay, and when you look at the log of this, you find that in fact it is minus n times the entropy of a quarter. So this typical sequence does have probability 2 to the minus n times the entropy. Okay, and in that case, the typical set is much smaller. Okay, although there are 2 to the n possible outcomes, the typical set is of size just 2 to the n times the entropy of 3/4, which is 0.81. Okay, so why is this thing true? Why is this property true? Okay, so we've drawn n samples from some distribution P. Okay, these are IID samples. Let's define a new random variable y sub I. And let's define it to be log 1 over p of x sub I. Okay, so this is a random variable. The way you do it is in the case of coin tosses, you flip a coin, you look at the outcome, heads or tails, and if it's heads, it's log 1 over the probability of heads. If it's tails, it's log 1 over the probability of tails. Now, one way we defined entropy was just as the expectation of this quantity. Okay, so the expectation of yi is just h. Okay, so we generate all these samples xi. For each sample, we've defined a new random variable yi, and the expectation of yi is just the entropy. Now, by the law of large numbers, we know that if we generate a lot of samples, then this average must converge to its expected value. Okay? So when you generate a lot of samples, the sum of the yi's is going to look very close to h. What does that mean? Well, if the sum of the yi's is within epsilon of h, okay, so this event is going to happen with probability 1 as you increase the number of points. Okay? Well, the sum of the yi's has a very nice form. The sum of the yi's is just the log of probability of x1 plus log probability of x2 plus log probability of x3. Therefore, it's just the log 1 over probability of the entire sequence, okay, since the points are drawn independently. And therefore, what this tells us is that the probability of this particular sequence is going to lie within epsilon of what we were calling the typical probability. It's going to lie within 2 to the minus n h minus epsilon and 2 to the minus n h plus epsilon. Okay, so this is another way in which entropy turns out to be a very natural, a natural notion of randomness. Okay, so let's return to our main question and see, now that we have a notion of randomness, we can actually try to formalize this question a little bit. Okay, so we had a large set, which in our toy example was just English words. We measured a bunch of features for each word. Okay, so for each word we defined, say, k features. The first feature was just that the word has length more than 5. Now we wanted to find a distribution over S. Okay, we wanted to find an assignment of probabilities to all the words that satisfied the constraints we'd observed. Okay, we observed that 30% of the words have length more than 5. So that satisfies these particular constraints, but otherwise is as random as possible. And now we can formalize that. We can say that what we want is something that has maximum entropy subject to these constraints. Okay, and this is called the maximum entropy principle. So now that we actually know a notion of entropy, we can actually formalize this as an optimization problem. Okay, and let's see what the problem looks like. So we are looking for a probability distribution P. It's over a set S, which is English words. Okay, we can think of this probability distribution as just a really long vector. Okay, so if there are 50,000 words, it's just a vector with 50,000 entries, which are all probabilities, and so they're all greater than or equal to 0, and they add up to 1. Okay, so we have this vector. Its entries are p sub x. That's the probability of x. We want them to add up to 1, and we want them all to be positive. Okay, so a reasonable probability distribution. We want to find the thing that has maximum entropy, subject to the constraints we observed. And the constraints were that the expected values of these features were equal to something. Okay, so for instance, feature 1, that's I equals 1, was simply 1 if the word had length more than 5 and 0 otherwise. And we wanted it to be the case that the expected value of that feature, the average value of that feature according to this distribution, was 0.3. Okay? So any questions about this optimization problem? Okay, so now that we have a notion of entropy, now that we have a notion of randomness, we can write it down precisely. So the nice thing about this is that the constraints turn out to be linear. The thing that we are solving for is P. Okay, we're solving for this vector. These are linear constraints. This is just a linear equation over here. So we have a bunch of linear constraints. These define some sort of polyhedron. And the function we are optimizing is a concave function. So this entire thing becomes a convex optimization problem. Okay? So convex optimization problem is just a generic term, which, I mean, even, you might say, okay, shouldn't this be a concave optimization problem? Well, maximizing a concave thing is the same as minimizing the negative of it, which is a convex thing. So we just call all of these things convex optimization problems. Yeah.
What is S exactly?
S is just the list of words in the dictionary. Okay, so if there's 50,000 of them, it's just the size of S is just 50,000. Okay, so this is the thing we now want to solve. Okay, now this was in the case where I had no prior knowledge at all. Okay, this was the alien who just arrived on Earth, and just had this dictionary with him, saw the list of words, and now wants to fit a distribution to this list of words. Okay? What if I had a little bit of prior knowledge? Maybe I have already constructed some statistical model that I'm reasonably happy with, but I looked at the model and I looked at this new data I have, and it doesn't really fit. So I kind of want to stick with that model, but I also want to tweak it to accommodate this new data, right? What happens in that case? So in that case, we have a prior pi, which is the previous statistical model that we cooked up in some way or the other. And now what we want to do is to find something that's close to pi. We don't want to go too far away from it. So we want to find something that's close to pi and yet satisfies these constraints that we've observed. Okay? So in other words, we want to find the distribution P that has the smallest KL divergence to pi subject to these constraints. Okay, subject to P, of course, has to be a normal probability distribution, and it should satisfy the constraints that I've actually observed. Okay, about lengths of words, etc., probabilities of different letter combinations. This is also a convex optimization problem because this function is convex. Okay, so I'm minimizing a convex function over a bunch of linear constraints. So one nice way to visualize the problem is to see it as a projection. Okay, so think of this whole board as being the simplex of probability distributions. Okay, so what is the simplex of probability distributions? It's all valid vectors. I'm looking at vectors of length 50,000. Look at the set of all valid vectors. In other words, all vectors of length 50,000 that add up to 1 and are non-negative. Let's call that the whole board. Okay. Now, I have some vector over here, which is my prior distribution, pi. Okay. I have some new constraints, and because they're linear constraints, they define a linear subspace of this simplex. Okay, so they define a linear subspace of this starting 50,000 dimensional space that I have. And what I want to do is to project the prior onto that linear subspace. Okay, so I want to find the point on that linear subspace that's as close as possible to the prior. Now, if the distance measure I was using was just Euclidean distance, then I would just kind of drop this point onto the subspace at a right angle. But it's not. I'm using this weird, KL divergence thing. And so I get kind of a curved distance instead. Okay, it's a different distance measure. You can't just plonk it down. You can't just plonk it down onto the subspace. Okay, so this is geometrically the problem we are trying to solve. We have our previous statistical model. Our constraints define a linear subspace in the space of probability distributions, in the probability simplex, and I want to project onto that subspace.
Why is Euclidean distance not a problem?
I beg your pardon?
Why is Euclidean distance not a problem in this case?
You could use the Euclidean distance, but we saw that the entropy is the most in our axiomatic framework, the entropy was the only reasonable definition of randomness. And so once we're using the entropy, then we have to use this. Okay, so if for instance, our prior was the uniform distribution, what we would want is the maximum entropy distribution in this subspace. And that would be the KL distance to the uniform. Okay, so our axiomatic framework has constrained us in that sense. Great, so this is our problem. And we saw that, so this is what the problem looks like geometrically, and we saw that when you actually write it out in terms of the equations, it turns out to be a convex optimization problem, and that is really useful. Okay, so why does it help to have a convex thing? Well, on the most naive level, it's convex, it looks like this, which means that there are no local optima. You have this global solution. But that's just the tip of the iceberg. The real thing is not just that you have that global solution, you don't have to worry about local optima, but it's that once it's expressed as a convex optimization problem, you can just apply some standard kind of deterministic machinery to characterize the form of the solution. Okay, so it's not just that we know that there's a unique solution and it's the global optimum, But it's that because it's convex, we can use various tricks to actually show that the solution has a very specific form. It's very easy to find out the form of the solution. Okay, so let's see how we do that. Okay, so here's the problem we are trying to solve. We're looking at all non-negative vectors. We're minimizing the KL divergence from pi. We have these linear constraints. There has to be a probability thing. It has to sum up to 1. Okay? So let's just apply the method of Lagrange multipliers. So we are minimizing this quantity. That's the KL divergence. We include a Lagrange multiplier for each of these constraints, and we have a multiplier for this constraint as well. So we have a total of k plus 1 multipliers. Okay? And now we take the derivative. So we take the derivative of this thing with respect to the thing we're solving for, p sub x. So we're actually solving for a whole vector. So we take the derivative with respect to one component at a time. Okay? When the smoke clears, this is what the derivative turns out to be. You have to set the derivative to 0. And when you do that, you find that the distribution has a very specific form. Okay? Now you can apply the law. You can do this Lagrange multiplier thing anytime you like, even when there are lots of local optima. But in the case of a convex optimization problem, you know that the solution has to have this form. Okay? So here's the form. It's the prior distribution that we started with, okay, times e to the linear function of the features. Okay? And then there's some normalizer in front. Because although this has summed up to 1, once you multiply it by this thing, who knows if it's going to sum up to 1 anymore. Okay? So you take your prior and you multiply it by this thing. And it turns out that this is actually a very, this is a very, very common type of distribution. And it's called an exponential family. This would be called the exponential family generated by pi. Okay? So the maximum entropy principle has brought us to the exponential family of distributions. Okay? And so let's look more at that exponential family. But first, let's just peek at what the form of our particular problem, what the form of the solution was for our particular problem. Okay? So we had this toy problem. And now when we look at this solution, what it's saying is that it looks like this. There's some normalization factor, so I'm just saying proportional. But otherwise, it has a very simple form. It's just e to the some linear function of the features. Okay? And this is just really convenient because a priori, we had no idea that the solution was going to be so convenient. After all, we were solving for a general vector of length 50,000. It could have been that the solution would require us to write it down as a table with a different number for each particular word. But instead, we got the solution that has this amazingly convenient functional form. It's something that we can express very compactly. And it's something that we can even, we might even be able to understand. Okay, so it's a linear function of the features. Okay, so what do these things mean? What do these coefficients, which, as we've seen, are actually Lagrange multipliers, what do these things mean? Well, for instance, if lambda 2 is 0.81, this means that if the word ends in e, then you jack up its probability by a factor of e to the 0.81, 2.25. Okay, so this is the sort of interpretation of these Lagrange multipliers. Okay, great. So, so we formulated this maximum entropy problem, and this worked out very well for us because it gave us a distribution that now has this very convenient functional form. Okay, and I said that actually the solution to this problem in general was just an exponential family. So what are these exponential families? What is this thing, exponential family of distributions? Okay. So it turns out that if you look at the statistician's grab bag of distributions, the distributions that pop up everywhere. The Gaussian is all over the place because of the central limit theorem. Poisson is all over the place because of the law of small numbers. The binomial, the Bernoulli distribution, that was that's the first and most basic distribution, just straight from the gambling tables, right? So all of these distributions turn out to be exponential families, okay? And what one would say is that the Gaussian is an exponential family of distributions. Each of them is a whole family of distributions. It's an exponential family. So what is this thing? What is this exponential family? How exactly is it defined? And what does it buy us to think of? What does it buy us to look at things in this generality, in the generality of exponential families? So let's define an exponential family. In order to do this, you need three things. First, you start off with some input space. Okay? Then you have some sort of base measure on the space, which you can think of as a prior. Okay? So actually, I have a little. This is actually a typo. You don't actually need the input space to be part of RR. It's just an arbitrary input space. It's just that the base measure would then have to be on this input space. Okay? And so what is the base measure? Well, you can think of it like the prior, but in general, for the time being, you can just think of the base measure as being 1. Okay, so you need an input space, you need a base measure, which let's just think of as being 1, and now you need to choose a bunch of features. And once you've specified these three things, you have an exponential family. Okay, so what do these things look like? Well, the exponential family generated by this particular base measure and this particular choice of features just consists of distributions of this form. Okay? Distributions where the probability of x is proportional to whatever the base measure is, times e to the linear function of the features. Okay? So each of these distributions is parameterized by a k-dimensional vector, where this k-dimensional vector specifies the linear combination of the features that goes into this exponent. Okay? Great. So, okay, so as it stands, this is looking, this is not even normalized. I haven't even, it's right now, it's just a proportion, right? So what do? We at least have to normalize it, right? So we have this input space, we've got a base measure, we've got our features, and we are saying that we're going to look at distributions of this form. Okay, so to normalize it, we have to stick some normalization constant in the front. Okay, and this normalization constant is going to be a different number for every eta. Each eta is a different parameter, and it defines a different distribution. So for each one, there's a different normalization. It turns out that the way we usually write this is actually to put the normalization in the exponent. So instead of writing it right in front over there, we pull it into the exponent, which is no problem at all, and we write it over here. Okay, so this g is the normalization term. Okay? So the g is set so that it's just so that everything sums out to 1. So it's just whatever we had otherwise, we just sum it up. Okay, so the normalization would just be the sum of all these things. That's what g is. And since we've moved it into the exponent, we have to take the log of it. And this thing is called the log partition function. Now, this thing is going to assume sort of larger significance later on. As it stands, it seems like this g is no big deal, right? It's just some number we got to stick in front to normalize the thing. Okay, but it turns out that this is going to have many interesting properties. Now, this sum might not even exist. It might be that this is infinite, in which case we can't allow that particular value of eta. So the natural parameter space is the set of etas for which are actually normalizable, okay, which actually correspond to valid distributions. So that's a natural parameter space. So let's look at an example. So I said to find an exponential family, you start with three things, and that uniquely defines the family. Okay, so let's look at, suppose I was claiming Bernoulli is an exponential family, right? So what are the three things we need? We need the base set, which we know is 0, 1, the base measure, 1, and we have some flexibility in the choice of features. But since it's just 0 and 1, the only feature that it makes sense to choose is t of x equals x. You can throw in other stuff like x squared, x cubed, but it's not giving you any extra information. Okay? And once we've chosen these things, the exponential family is uniquely defined. Okay? After this, everything's set, it's deterministic. So we set these things down, and now let's look at the exponential family we get. Well, we know the functional form is going to be that we're going to have these distributions indexed by eta, and the probability is going to be proportional to e to the eta x. Okay? Okay, so now we need this thing to normalize. So, well, x has only two values, 0 and 1, so we get e to the 0 plus e to the eta. So our normalization factor is just the ln of this, the natural logarithm of this, and this is the log partition function. Okay? Any questions about this? Great. So this turns out to be defined for all etas. Okay, we never have to worry about this being infinite. And therefore, the natural parameter space is simply the reals. So let's look at the distribution. Since the parameter space is the reals, let's look at the distribution we get when we have parameter eta. Okay? When we have eta, the distribution looks like this. It's e to the eta x, and we have to multiply by the normalization constant, which is this. Okay? In other words, the probability of a point 0 is just 1 over the normalizer. The probability of 1 is e to the eta over the normalizer. Certainly a bona fide Bernoulli distribution. Okay? So the only problem over here is that although this is a Bernoulli distribution, we are not used to these parameters. Normally when we specify a Bernoulli, we specify it according to the heads probability. Now we have this weird formalization in which it's specified according to this so-called natural parameter that's actually a number between minus infinity and plus infinity. So what's the deal over here? You know, so there's this natural parameter, and certainly it specifies all the Bernoullis. Any Bernoulli distribution can be written this way. If you want this to be your probability P, you just solve for eta. That's no problem at all. But the parameterization is not the one we're accustomed to. We're accustomed to parameterizing this between 0 and 1, not between minus infinity and plus infinity. Okay, and so if you look at the thing over here, the natural parameters lie in the range from minus infinity to plus infinity. And minus infinity corresponds to a coin with bias 0. Plus infinity corresponds to a coin with bias 1. Okay? And there's this mapping from these natural parameters to the parameters we are more used to, the actual bias of the coin. So the weird thing about these natural parameters is that although they're the ones that are mathematically natural, they don't actually necessarily correspond to the parameters that are natural for us. So we end up having these two different parameter spaces when we talk about exponential families. We have the natural parameters, which is the space that the models themselves want. This is the one that the math wants. And then this is the one that's more convenient for us. These are the expectation parameters. These are the actual mean of the distribution. Okay, so in exponential families, we're always juggling these two spaces, and there's a one-to-one map between them. Okay, and you can see this particular map over here. Let's look at another example, and which we'll derive in a different way. Okay, so now let's look at a Poisson distribution. Now, a Poisson theta distribution is a distribution over integers, or a distribution over non-negative integers, and it has mean theta and variance theta as well. Okay, it's got the same mean and variance, and this is the functional form of the distribution. The probability of any given x, which in this case is a non-negative integer, is e to the minus theta times theta to the x over x factorial. Okay? So why is this an exponential family? Okay? In order to show that, we kind of have to massage it into the right form. So let's try and rewrite it. Well, you can write it like this. Theta to the x is e to the x ln theta. We get the minus theta. And now it looks much more like an exponential family form. This is the base measure over here, the h of x. This looks like, this is just some linear function of x, which is exactly the form we wanted. Okay? So now our base space is the non-negative integers. Our base measure is just 1 over x factorial. And our feature is just x itself. We just need a single feature. Okay? So now when we find the log partition function, so once we've specified these three things, we know the rest is deterministic. We know that the functional form must be this. And to find the log partition function, we just normalize. We just sum this over all possibilities. Okay. Well, this is quite an easy sum because it looks like the Taylor series for e to the Taylor series expansion of the exponential. So it's just e to the eta. Okay. So the log partition function is just e to the eta. And once again, we don't have the natural parameters. Okay. Once again, our natural parameters are not the ones we're familiar with. The natural parameter space occupies the entire real line. And the ones we're interested in are actually e to the natural parameter. Okay? So in this case, the natural parameter is ln of theta. Okay. Okay. So let's do one more example. And this one's a little trickier because we need more than one feature. Okay, so say we have a Gaussian with mean, mu, and variance sigma squared. So this is the form of the Gaussian. And now we want to write this as an exponential family distribution. If you expand out the square, you end up with terms both in x and x squared. So you need to pick two features. X has to be a feature, and x squared also has to be a feature. And if you pick both of these, then you can write the exponent as a linear function. Okay? So in this case, our base set is just r. Our base measure is, for convenience, I've set it to 1 over 2 pi. I could just make it uniform. Constants don't matter. And I need to pick two features now. For this, it's not sufficient to just pick one feature, so I pick x and x squared. And now just from this, I can read off what the natural parameter is going to be. Okay? And once again, we can compute the log partition function. And in this case, the natural parameter space is r times r minus. Okay. So fine. So there are a lot of these distributions that are clearly important standard distributions. And we found that these can be coerced into the exponential family form. Right? But what does it buy us to actually deal with this formalism? Is it the case that when we first looked at the exponential family thing, it looked like it was really specific. It's, what kind of distributions could possibly have that form? Now it seems like it might be too general. We've effortlessly expressed the Bernoulli, the Poisson, the Gaussian as exponential family models, right? Is it so general that it's not useful for us? Why are we... what's so good about this exponential family? What is special about exponential family distributions? And it turns out that a lot of the special properties of this distribution lie where one initially would not expect it to lie, namely in the log partition function. Okay, so the way this log partition function came about is that it was just the normalizer. It was just the thing you kind of tack on in front to make it all add up to 1. However, it turns out that this normalizer actually contains a wealth of information about the distribution. Okay? And we're going to use its properties quite heavily when we get back to maximum entropy. Okay, so first of all, it turns out that this thing is strictly convex. Okay, so for instance, the Poisson, in the Poisson case, it was e to the eta. Okay, so it was the exponent which is, which looks like this. It's a strictly convex function. Okay? Among other things, it means that its derivative is 1 to 1. Okay, so if you have a strictly convex function and you look at its derivative, well, the derivative is increasing. It's a 1 to 1. It's a 1 to 1 function. The derivative actually has other properties. The derivative turns out to simply be the mean of the distribution. Okay? So if you take the derivative of this log partition function, so this log partition function, you just compute its first derivative, and that turns out to be the mean of the distribution. The expected value under random draws from that distribution of the feature vector. Okay, so why is this the case? Well, in general, the feature vector has many components. There's eta 1, eta 2, so on. Let's take the derivative with respect to the ith component. You take the derivative of this with respect to eta I. Well, the derivative of log x is just 1 over x dx. So it's 1 over this thing times the derivative of the top, which is this. Okay, and now you can see that it's just the probability of, so it's just the expectation of that particular feature. Okay, and if you do the similar thing for the second derivative, you get the variance of the distribution. Okay, so just by taking the first derivative, second derivative of the log partition function, we end up getting the moments of the distribution. Okay, so there's a wealth of information contained in this log partition function. Okay, so what else? In what other ways is this exponential family unique? Okay, what is special about, why have we singled out these distributions as being important ones? What else is unique about them? So the real benefit comes when you start looking at maximum likelihood estimation. So suppose you're dealing with some exponential family, okay? And as we've seen, to specify an exponential family, you just specify the base measure and the features you're going to look at. So suppose we're dealing with some exponential family, and now we see a bunch of data, and we want to find the best member of the family. Okay, so for instance, we see a bunch of points, and we want to fit a Gaussian to them. So let's find the maximum likelihood choice of the parameter. Okay, so you just plug into this. We want to maximize the log likelihood. So take the log of this. It's eta times t of xi minus g of eta plus log of h of xi. You rewrite it because you can pull the eta out. Okay, and you get the sum of these ti's. And this is just a constant. And now you get the sum of the log h of xi's. And to maximize this, you set the derivative. And you take the derivative, you set it to 0. Well, if you do that, what you're doing is you're setting the derivative of the log partition function to simply the average of the data you saw. And that's the maximum likelihood choice. Okay, we saw that the derivative of the log partition function is simply the mean of the distribution. So the maximum likelihood choice is very simple. You just take all your data, you take the average, and now you pick the model that has exactly that same mean. Okay? So, so this is, so this is why these models are so useful. In a lot of modeling contexts, when you have a lot of data and you want to fit a model to it, you actually need to keep the data around. If you're fitting a linear classifier to it, you need to keep all the labeled points around, and you give it to some sort of, you give it to some routine that juggles them and spits out a linear classifier. In these exponential family models, you can have a vast amount of data, but you don't need to keep it around. All you need is the average. And once you have the average, you can find the best fit model without any problem at all. Okay? So these exponential family distributions are the ones that in order to fit them, you just need to keep the average of the data. Yeah?
Does any distribution that has statistics fall under exponential?
Yeah, modulo some niceness conditions, etc. So, okay, so let's look at an example. So you have a bunch of data, and you find that the mean is 7.5. What Poisson should you fit to it? It's easy. Whatever Poisson has mean 7.5. Okay. But this is where a little problem comes up between the two types of parameterizations of these distributions. Okay. The one for us, it's fine to say, yeah, we're just going to pick the Poisson with mean 7.5. But that's not the natural parameter of these Poisson distributions. Okay, so what is the natural parameter for the Poisson which has mean 7.5? Okay, so in the case of Poisson, it turns out to be easy. We know that the log partition function is just e to the eta. So the derivative is also e to the eta. Okay, which means, and this is the mean of the distribution. So we just set this to be 7.5. And therefore, eta is ln 7.5. Okay. So in the case of the Poisson, it's easy to go from the expectation parameter, which is 7.5, to the natural parameter. That's just the natural logarithm of 7.5. But in general, it's not always easy to invert this function g prime. It's not always easy to say, okay, these are the means I want. What is the corresponding natural parameter? That can be a hard problem. And if we look back at our problem, unfortunately, that's one of these. Okay? So, we know what the expectations are of all of these features. That's what we started with. We know the expected value of this is 0.3. We know the expected value of this is 0.4 or whatever. But that doesn't help us in figuring out what these parameters should be. How do we find the setting of these parameters that gives the right expected value for the distribution? Okay, this is not an easy problem. And so the way to think of these two spaces is that we have this natural parameter space. These are the parameters we want. But the space in which the data lies is a different space. Okay, and we can compute averages in that space. So we compute averages and we got this, So maybe we had a data point here, one here, one here, one here, one here, and we computed the average and we got this. Okay, this was this is just the average of all the data. And now we want to go back and we want to find the natural parameter that corresponds to that. And that's not an easy problem. Okay, we've got this one-to-one map. We saw that G prime is a one-to-one relationship because G is strictly convex. But it's hard to go backwards. Okay? So in summary, when you have when you're dealing with exponential families of distributions, finding the maximum likelihood distribution is in some sense an easy task, but only if you're using the expectation parameterization. If you're just looking for an expectation parameter, it's the easiest thing in the world to fit one of these models. You just set it to the average of the data. But if you're looking for natural parameters, then it's a little harder. It becomes a convex optimization problem. So why is it a convex optimization problem? Well, let's go back to the equation. This is what we are trying to solve. We're trying to maximize this quantity. Well, we saw that G is strictly convex, and everything else is just linear. So maximizing this equation, this is a convex optimization problem. Okay? So the problem we want to solve, the parameters for our model over here, this is a convex optimization problem. And this is the thing that we were calling information projection. Okay? So let's see how you actually solve this problem. How can you go about solving this thing? Okay. So just to kind of recap and just to step back a little bit, how did we get to this point? Okay. So we started with a problem which was a maximum entropy problem. Okay, we have this toy problem. We want to fit a model that makes as few assumptions as possible subject to given constraints. We found that the solution to maximum entropy problems are always exponential families of distributions. Okay, and now we actually want to solve for these distributions. Okay, so here's a general form of the question we started with. We had a bunch of priors. We had our prior knowledge. Okay, this is our earlier statistical model. Now we have some observations that we make based on, say, a small sample of data that we collect. And now we want to update our prior. We want to choose a distribution that's really close to the prior, but also satisfies these constraints. And it turned out that the solution to this is to choose the distribution to be an exponential family model. Specifically, the solution to this is the unique member of the exponential family generated by pi and t, which actually satisfies, which has the given expectations. Okay? So pi and t, the prior pi, and the features t uniquely define an exponential family of distributions, and we just have to pick the one that has the given expectations. Okay? So let's look at an example of this, right? So suppose I just tell you that, look, there's some distribution, and I know its mean is 0, and the expected value of x squared is 10. What distribution should I choose? Now, of course, there's infinitely many distributions that have these expected values. Okay, there's no shortage of them. But if you were to make the maximum entropy choice, the answer is very simple. Okay, we have a distribution over R. Okay, so that's our base space. We found two expectations, so the features we want are x and x squared. Okay, this generates the Gaussian. These are the features that generate the Gaussian family of distributions. So now all we have to do is to pick the Gaussian that has this mean and this expected value of x squared. In other words, this variance. Okay, and that's just the Gaussian 0, 10. Okay, so this is the maximum entropy choice. So if you were following the maximum entropy principle, this would be the distribution that you would pick. Okay, yeah. Yeah. Yeah, so over here, implicitly, I've chosen a base measure that is uniform. Okay, that's just flat, because the base measure corresponding to the, you're right, that in order to uniquely specify an exponential family, I need not just the choice of features, but also a base measure. And here I've just happened to I've just chosen a base measure that is 1 everywhere. Okay, the Lebesgue measure on the real line. Okay. If you had a prior over the space, then you would choose that as the base measure. And then you might end up with something different. Okay, something that, in particular, you might end up with something that's not a Gaussian. Okay, so any questions about that? Okay. So now let's figure out what the solution has to look like. Okay? So we have some sample space, we have some features, we have some constraints, and we have a reference prior. So here's the key statement. Okay? So the claim is that if there's a distribution of this particular form that happens to satisfy the constraints, then it is the unique minimizer It's the unique the unique distribution that's closest to pi subject to these constraints. Okay. And now let's see why this is the case. Okay. So if you can find a distribution that looks like this that actually satisfies the constraints, then that is the unique solution to our problem. Okay? Why is that? Well, let's say P star is this unique distribution. Let's say P star is a distribution of this form that satisfies the constraints. Let's show that no other P can possibly do so. Okay? So we have some distribution P star that has the exponential family form. Okay? And it satisfies the constraints. We'll show that any other distribution which satisfies the constraints must be further away from pi, must be strictly further away from pi. Okay? So why is this the case? Well, let's look at the distance. Let's look at how close this other distribution is to pi compared to how close our exponential family distribution is to pi. And we'll show that this quantity is strictly positive. Okay? So let's just expand out these terms. K of P pi, well, that's just the definition of KL divergence, and we do the same for P star. Okay? Now, for the next line, we just copy this over, and we notice that P star, because of the exponential family form, we can write P star over pi very simply. P star is equal to pi times some e to the linear function. Therefore, P star log P star over pi is just eta dot t of x minus g of eta. Okay? So we saw that P star is of this form, so P star over pi is this very simple linear function. Okay? Great. Now, because we boiled it down to a linear function, we know that the expectation of this linear function under P star is the same as its expectation under P. Why? Because, well, okay, this part is just a constant, so we don't care about that. This part is equal to eta times the expectation of t. And this is, so the expectation of t is the same under both distributions because we know that they both satisfy the constraints. The constraint is that the expectation of t is equal to b. Right? So therefore, the expectation of t under P star is equal to the expectation of t under P. And so we can make this switch. Okay. So now when we move further down, we can now swap back. Well, the way we got this in the first place was as log P star over pi. So we get that back. And now it's very convenient because we have p's in the front of both of these. And these pi's cancel out. And what we end up with is just the KL distance from P to P star. Okay? So we get this very interesting relation. We get that the difference of these two KL divergences is exactly this third KL divergence. And since P and P star are not the same, this is strictly positive. Okay? And therefore, P is strictly further away from pi than P star is from pi. Okay? And that's why P star must be the unique minimizer of the distance to pi. Okay, so any questions about this? Thing? This one relation turns out to be extremely useful for us. We've now derived this relation that the distance from P to pi is just the distance from P to P star plus the distance from P star to pi. Okay, and this is let's see what this looks like geometrically. So when we go back to the geometric picture of our thing, so recall that this whole page is the simplex of probability distributions. Okay, so this whole thing, this whole big thing is the simplex of these probability vectors, which are say 50,000 dimensional. Okay. We had some prior distribution, some prior vector, and we wanted to project it onto these constraints. We wanted to find the vector closest to this which satisfies the constraints, and that's the I projection. Now we see this interesting relation. We say that pick any other point that also satisfies these constraints. In other words, pick any other point on this affine subspace of the simplex. Right? Then we have the relation that the distance from, we have this relation over here, the distance from P to pi is equal to the distance from P to pi star, from distance from P to P star, plus the distance from P star to pi. This is quite remarkable because this is a Pythagorean theorem. This is exactly the same relation we have when we're projecting with respect to Euclidean distance. So suppose that instead of using KL distance, I was projecting with respect to squared Euclidean distance. Okay, so then I would just project right down over there. I'd get that right angle. And then if I looked at any other point, then I'd have this right angle in the middle. And I'd know that, this distance squared plus that distance squared was equal to this distance squared. Okay? So amazingly, that same Pythagorean relation holds even when one is not using squared Euclidean distance. It holds also for KL divergence. Okay? So you take any point, you take its projection onto a linear subspace. Because we are using KL divergence, we have a special name we call it I projection, for information projection. Because instead of using a normal distance measure, we are using this information theoretic distance measure. But you end up with this same Pythagorean relation. Okay? So this is the geometry part of the thing here.
Does this rely on one part of that actually being an exponential? I mean, you can't do these arbitrary distributions.
Sorry, does it rely on what?
It's relying on one of the p's as being where the exponential is, right? Of course, the other don't.
Oh, the P star. Yeah. So this is not just in the exponential family, but this is the projection. So P star has to be the projection of pi. And that's also true in the Euclidean case. In the Euclidean case, the Pythagorean, if you're projecting onto a plane, the Pythagorean theorem only holds when you're pivoting on the projection of the point onto the plane, right? So you get the right angle. So this is literally the generalization of the Pythagorean theorem in the Euclidean.